Hello again. So let's look at the next in our list of Alkyne problem examples. And for this one, we are faced with the original ethine being converted in 5 steps or less into this extended structure with an alcohol group that's also popped up in the molecule. So as usual, first thing to think about is, where is my original molecule in that final product? Now this one is a little bit easier because we see that carbon to carbon triple bond in the molecule. So that triple bond there is probably the triple bond here that we started with. So we can start to think about how the molecule has changed and the jigsaw pieces of the reaction that go together with the greater whole in these 5 steps. So first thing that probably springs to my mind is, when I look at this, that alkyne must have been reacted at some stage with some sodium amide, which will strip off a proton. Remember, with that triple bond, there's carbon to hydrogen bonds on either side of the molecule at this point with hydrogen. And those hydrogens are acidic, we said. And so a strong base like sodium amide could pull off one of those hydrogens with the alkyne reacting like an acid, and it would create an acetylide ion. An acetylide ion which could then react in an SN2 mechanism with an alkyl bromide. The atom attacks at the bromine here, or at the carbon, and the bromine drops off, and we extend that carbon chain. Two steps, but I'm being lazy and showing it as just one single step. So the amide pulling off a proton, and then that ion produced attacking the alkyl bromide here, and the bromine drops off and it will extend the molecule. So that explains one side of the molecule as it's seen. Now on the other end, we must have extended the molecule again, but it's a tricky one, because how do we extend the carbon skeleton and get this alcohol group produced as well? Well, we looked at a couple of examples of these SN2 reactions in the alkyne chapter, and as well as reacting with alkyl bromides, we briefly talked about a reaction with sodium amide, again to pull off the proton, in this case on the other side, pull off the proton, and then react it with an aldehyde or ketone. That acetylide ion produced would use its electrons to attack the carbon at the bottom end of the carbonyl bond, and that would pop open the pi electrons and send them back to the oxygen. So after that sodium amide attack on the acetylene, and then the acetylide ion attacking the aldehyde, we produce this alkoxide structure. And we could then add in some acidic conditions, some hydronium ions like from hydrochloric acid or sulfuric acid, and that acidic condition would protonate the alkoxide group, and we'd finish up with the alcohol. So a 2-step reaction, we could maybe even consider as a 3-step. The sodium amide first, together with the aldehyde, to produce this alkoxide as we produce this new link, and then hydronium ions to protonate. Now sometimes this is all written down as one single step of a reaction. So you'll see the alkyne and it will say the sodium amide first, then number 2 would be the aldehyde, and then number 3 would be acidic conditions. And just be aware that that is sometimes described as just one single step of a reaction, but we're breaking it down for the purposes of this particular example. So there's all the things which collectively have to happen to get to our final product. So let's retrosynthesis this molecule back from the final material back to the original acetylene. So the last thing we probably wanted to do was protonate that alcohol group with acidic conditions. So we must have started previously with the alkoxide. Now there's a good reason we want to get this alkoxide addition last, rather than starting with the alkoxide and then going to the extension on the other side, which we'll see in a minute. Because to produce that alkoxide, the previous step, as we had just seen, must have been the sodium amide with the aldehyde. If we haven't already alkylated on this side of the molecule, then the addition of the sodium amide could cause that hydrogen to be popped off from this side, and it could muddy the waters and produce a mixture of products. So this is one of the last things we've got to do. That sodium amide will take us back to this previous step, and we're specifically removing the proton from here instead of removing it from here, which could create an alternative reaction path. So by the time we add sodium amide with the aldehyde here, we've already blocked off this side of the molecule. So previously we must have reacted with the alkyl bromide, and that would have reacted with the original acetylide ion, and that acetylide ion of course would have been produced by an initial reaction with the starting material with sodium amide. So the sodium amide takes off a proton from the original reactant. That creates the acetylide ion. We can then react it with the alkyl bromide to extend on one side. Then with that side blocked off, we can react with more base to remove the proton from the left hand side. It then reacts with the aldehyde. We produce the alkoxide, and then acidic conditions to protonate. A full reaction done in reverse.